In this example, we see a capacitor which is connected to a battery. It's not turned on yet, but when we turn it on, you can see that the moment it turns on, the top plate charge will increase, and you'll see an amount of coulombs being accumulated on that top plate. So capacitance is like the size of the tank, if you will. We can adjust that by moving the plates together. As you can see, if we slide them together, you can see the amount of capacitant charge increases to about half a picofarad there, which we'll leave it in that general vicinity. If I wanted to make a further adjustment to it, I could increase the plate size as well. So here I can get it to nearly a whole picofarad. Let's leave it around about that picofarad. Now, as soon as I turn the battery on, you'll see the top plate charge indicate at the moment there's no coulombs. So as soon as I turn this on, we'll crank this up to about 1.5 volts. And you can see there that the plates themselves have got positive and negative electrons accumulated on them. So if I wanted to see even further things, I could actually put the little indicator on there to show the electric charges going, well, between positive and negative. Of course, theoretically there's an electric charge or electric pressure there. There's no flow of current at this point in time because it's a capacitor. It's, according to DC, an open circuit. So I put my voltmeter on here. You can see that the voltage sits at 1.5 volts. What happens when I take the battery off it and I drop this back down to 0? You'll see that the voltmeter is reflecting 0 volts. But what if I charge it back up again now, and then I disconnect the capacitor from the power supply? So what's the voltage now? Well, it's still 1.5 volts, well, a little less than that, 1.45 volts. So this is now acting as the battery, and it will do so until such times it finds a place to discharge. Hope that helps. In this lab we've attached the capacitor to the battery, and we also have a light bulb in circuit here. So again, we'll charge up the capacity on the battery. We'll charge up the coulombs on the battery by increasing the voltage over here and ensuring that there's some coulombs in there. We can increase and decrease it by increasing the size, of course, and crank that all the way up, and by decreasing the gap between the capacitors. And we'll get it about 1 picofarad, 1.5 picocoulombs. So once we've done that and we disconnect this, I'll put the voltmeter on here as well, just to show you what's going on here. I'll put that over here and over here. So at the moment it's showing 1.5 volts. If I disconnect the power supply, it still stays at 1.5 volts over the capacitor. So it is acting like a battery. Now what happens when I connect up the capacitor to the light bulb? As you can see, it's instantaneous discharge of the charges which are stored on the plates, because now the plates have got a route for the current to go, and until all of that charge is dissipated, there's still some current and some voltage until it gets back down to 0. So again, by putting it in a neutral position, maybe I can increase or decrease the amount of coulombs in this instance, or capacitance in this instance, by making a little bit of a bigger charge plate available for the charge when it comes on. When it comes on, of course, it charges up now, 2.6 picocoulombs. Again, the time that this takes is relevant to the time constant, to the amount of resistance in the circuit. There wouldn't be a lot in this particular example because of the fact that there's only the wire resistance. And once we discharge again, you can see again an instantaneous discharge of the capacitor through the light bulb until it gets back down to 0. Look at the electric fields. You can see them dissipate slowly till such times it gets to 0. Now you notice the capacitance is still 1.77 picofarads. The thing that changes here is the amount of coulombs charged on the plate, because we've discharged it now. We've discharged it to a point where it gets to 0. Hope that helps.